I worked at Argonne National Laboratory for most of my career, largely working on the PETSI software system, and much of my research is focused on scalable algebraic solvers. I would say in a few weeks I'm giving a really gentle introduction to PETSI at the CCM Wednesday morning seminar, so anybody who's interested is welcome to join that. Okay, so let's start with the simple model problem. What we want to focus on here is we have an objective function that depends on, in this case, the final solution to time-dependent ODE, as written here. And we want to minimize this function. So we want to get some gradient information out efficiently for this function g. And in this particular case, we're going to use as our parameters the initial conditions u sub 0. Now, there's a variety of other cases that also exact same techniques work for. So we can have parameters p that f depends on, that we want to differentiate with respect to. Our objective function can depend on all time, not just the final solution, or our objective function can depend on particular times inside where maybe you have data. And you can also do this for more general ODEs, doesn't have to be written in this form. And the ODEs often may be coming from a PDE problem. So there's two complementary approaches for doing this, and I'm kind of making up my language here, but I'm calling the first one algorithmic differentiation. And in that, what you do is you have an algorithm and you want to get the derivative of the computation of the algorithm. So you manually take that algorithm, compute the derivative, you massage that, possibly a lot of massaging to get something that's higher performance, and then you code that. And I'm distinguishing that from automatic differentiation, where you take your algorithm, you code it, and then you use a system that runs through that code you've produced to give you the derivative information. A lot of similarities between the two. Once you understand the basic concepts of one, you understand the basic concepts of the other approach. And as we saw in one of the talks yesterday, often you actually want to use a combination of these two things. And I'll say a little bit more about that at the end of the presentation. So let's start. We know how to compute derivatives. We know the derivatives for elementary functions. We know the sum and product rules. It's all very straightforward. The only one that's interesting is the chain rule. And it leads to the complications that you hear about and think about with these methods. And one thing I'm going to do, as you'll see later, is I'm going to try to distinguish between the discrete case and the continuous case, and show how they're actually almost exact parallels with each other. One, you just use summation by parts, and the other you use integration by parts to get the end result. So let's go through the completely naive thing to do. Let's just say we have a function that we're evaluating 3 times, so it may be 3 steps of a ODE integrator, something simple like Euler, or something more complicated like 4-stage Runge-Kutta. Almost anything can go in there. And I want to find the gradient for that. So I just use the chain rule, and as written, it looks pretty simple. We just have to evaluate this G prime at the final time, multiply it by the Jacobian at the previous time, multiply it by the Jacobian of f at the previous time, and multiply by the Jacobian of f at the initial time. But let's see what happens computationally if we start in this end of things. We'd form the first Jacobian, and then we form the second Jacobian, then we do the product. Form the next Jacobian, do the product, form this final G, do the product, and we're done. But that's, of course, very expensive because we're doing matrix products all the way through. It's no reason to do that. It's very nice. Is what we'll do is we'll just actually apply the operation in the reverse order. So we'll start with the 3, form the last of the Jacobians, and apply the transpose of that to the operator. That gives us a vector result. Form the next Jacobian, apply the transpose, again and again. So we're only carrying through the vector. We don't have to carry through the matrix-matrix products. And for large problems, of course, is an enormous difference in performance. So just written down, this is called the adjoint method, or sometimes the reverse mode method. There are some problems with this in that you need to know the various U's in order to calculate the Jacobians in the reverse order. So this is done via what's called checkpointing. And there's a lot of really good work on checkpointing to minimize the number of checkpoints. And you don't actually have to checkpoint everything, because if you have certain values, you can find the intermediate values by doing a little quick integration from the point that you have checkpointed to the point that you need. And there's an algorithm that was developed, I don't know, quite a while ago called Revolve that gives an optimal procedure if you're checkpointing in, say, just memory, for how to reuse your checkpoints. You don't want to do something naive like just checkpoint at equally spaced intervals and then use those values and then back up and no longer reuse them. You always want to use all that checkpointing space available. And the Revolve algorithm is a way to do that. There's also algorithms where you checkpoint both in memory and on disk, trying to use the memory as much as possible and only minimally putting on disk if you need to have a very long history and so forth. And these algorithms are available in libraries, so you don't really have to reproduce them.
So Barry, could I ask a question? Is what you're calling checkpointing here what other people are calling taping?
So taping is actually, in particular, when you do automatic differentiation, and it's managing the moving back through the entire differentiation. So not just calculating the Jacobians, but also doing the elementary functions, doing the additions and multiplications. So taping is not only saving the history of the solutions, is actually saving the steps you do to compute it. So it's even more intense. And you don't need to do that when you're doing algorithmic differentiation. So let's now take this and apply it to using Euler's method for ut equals f tilde. And notice that my ODEs are always defined with an f tilde, while the f is the ODE integration scheme, or the thing that I'm chaining. So we just write down a step, and we know we need to find the derivative of f. So we just plug that in, and then we can take that and put it into the formula from the previous slide and see that, well, GI is going to be obtained by this quantity, where we have the f tilde transpose, and then the GI plus 1. Now, the remarkable fact is that this is actually the same as applying Euler's method for the linear ODE given here, with an initial solution at the final time given by g prime of ut at the final time, and the f is transposed, and then there's a minus sign. And the transpose comes from the previous argument on the previous page, and the minus sign comes from the fact that you have this I term and an I plus 1, and to get it back to GT, you flip the GI plus 1 and GI. And in a couple of slides later, I'm going to show how to apply this thing more generally to the continuum ODE problem. But let's see graphically what's happening here is we're first solving the ODE going forward. Then we're calculating this final G. And then we're solving the adjoint ODE back to the beginning, and the result of that solution is the gradient that we want. So let's do the same thing for backward Euler. It's a little more involved, but it's basically the same thing. We have our formula for ui plus 1 in terms of ui. So the f now is defined implicitly because we need the f in the evaluation of the right-hand side for backward Euler because it's an implicit method. But we can still find its derivative easily. So we calculate the derivative, and there's the derivative in terms of the f tilde prime. And then we can go ahead and write what GI is, and then go back and interpret it. It's backward Euler for the same equation. And so this is generically true, whatever scheme you're using for your numerical integration. Yep.
The mic, please.
In your third line, you have ui plus 1.
Yep.
How do you have that then? Like, why do you have access to that there? Like,
when I'm going back, I need to have the history of the u's in order to evaluate the Jacobians. And so I either have it checkpointed or I recalculate the ui plus 1, and then I can calculate the Jacobian from
got it. Yeah, okay, yeah. I forgot that you're on the way back. Okay, yeah.
Now, there was actually a very clever trick in the presentation yesterday where if you're using certain schemes like Leapfrog that are reversible, you actually don't even have to keep the history because you can actually back up and get the old solutions from your current solution. But generally, that's not true. Okay, so now what I'm going to do is I'm going to back up for a minute and derive the same formulation as before, but in a slightly different way in order that I can apply it also directly to the ODE. So I think about that. I'm going to do the same minimization, but I'm going to use Lagrange multipliers in order to do the minimization. Do you have a question?
Well, I guess what I was going to ask is, okay, with the setup here, little g is of the same size as u was.
Yep.
Is that right? It's a sort of transpose, but it's
yep.
Because you're only considering because your big G is a scalar quantity.
Yep.
Okay, so
I'm considering the very special case where big G is a scalar, and I'm integrating a nice full ODE.
Right. And does
all these techniques can be extended to all kinds of other possibilities.
Right. Is the fact that the backward ODE is linear, but the forward ODE might not be, does that mean the backward one can be easier or faster to solve? Or?
That's a good question. For explicit methods, generally it means the backward is slower because you actually have to apply the Jacobian, which is usually more expensive than just applying the functions in the forward.
Okay.
But for implicit methods, it's going to be faster because if you're when you're moving forward, you actually have to solve a nonlinear problem at each step, while when you move back, you're only solving a linear problem. And we see this in practice, actually, that exactly this correspondence, that getting that gradient information for an implicit is actually less expensive than getting the forward information. And that's something that's really valuable to keep in mind, and is, maybe only been understood in the last 20 or 30 years, that getting gradient information need not be that much more expensive than doing your simulation if you rig everything right.
Thanks.
And if you forget that, then people tend to not want to get the gradient information because they think it's too expensive. Okay, so this is elementary calculus 2 here. We write out the Lagrangian. There it is. We just reorganize terms. This corresponds to summation by parts. I just reorganized the terms so that I have the U2s together and then the U1s together. So taking the derivatives will be a little more straightforward. I first get the, take the derivative with respect to the U3s, then take them with respect to U2 and U1, and I get the same same formulas as I had before, not written in the transposed way. Now what I'm going to do is I'm going to consider the continuum case where we actually have the ODE directly. So where our Lagrangian is going to be g of u at the final time minus the integral of the Lagrange multipliers transpose times our ODE. And then I'm going to do a simple integration by parts on the first term. So that results in the final g at the final time times u at the final time, plus the values at the beginning time. And the sign gets flipped here, and the derivative simply moves from the u to the t, and this term remains the same. So now, again, corresponding to the discrete case, that gives us this equation for the final time, and then the equation for all the intermediate times, which corresponds again to what we had before for the discrete case. So this brings up another important concept. If we just go back for 1 second to, whoops, I don't know what happened there. I know, wrong direction, yeah. We see that we actually have a choice. We can take our algorithm, our numerical algorithm, and differentiate it and use that as our derivative, or we can take this continuum adjoint problem and code that to solve to get the gradient information. Now, they're not always the same because you have a lot more freedom with your continuum adjoint problem. You can actually integrate it in a different way. You could even use a different scheme. You could use different time step. If you use a different time step, then you have to interpolate the values that you have from the forward direction in order to evaluate the these f's as you step back. And so the approaches are called continuous and discrete adjoint. For a while, because the technology for discrete adjoints was a little primitive in automatic differentiation, I would say, there was a tendency for people to want to use the continuous approach. Now I would say there's probably less reason to. One of the advantages for simple situations for using the discrete is that you know that your gradient is actually consistent at the algebraic level with the function evaluation. So if you're using a standard optimization scheme, you have consistency. It need not be consistent always when you're using the continuous adjoints. And so you may get things where at the algebra level, your gradient is no longer a descent direction, for example, for the problem, even though, of course, at the continuum level it is. All right, now I'm going to show you the same thing holds if you have a parameter that you want to find gradients with respect to, or any number of parameters. We go through the same process as before. We simply apply the chain rule to this beast. Gives us something like this, where we now have the extra term that comes from the derivative of the f's with respect to the parameters. But if we reorganize things again, looking at the ODE, you end up with, in this case, something like this, where the same term appears as before, but you get an additional forcing term that comes from the derivative of the f tilde with respect to the parameters. And the libraries like PETSI that implement this, they have full support for this. So you can do this type of analysis as well. So going back then to my second slide, what about computing the actual Jacobians of the f that's in your ODE? Well, you can do that, of course, or you can provide code that does the matrix vector products, because you may not need the actual Jacobians. And if there's efficient forms for computing the application of the Jacobian, then generally there you can play around a little bit and get an efficient form for applying the transpose of that Jacobian as well that you need for the backward one. Or you can use any of the tools for automatic differentiation to get these things for you. So you can use AutoDiff, ADLC, you can use the stuff in TensorFlow and so forth to achieve that. Finally, I just wanted to say that I don't know anything about machine learning and back propagation, but my understanding is that the procedure is more or less is doing the same thing for you. Yeah. I actually have run out of material. Here's further reading. Paper we've done where we discuss how we've done all of this for PETSI. I could say that it's also possible to get second derivative information. So in PETSI, you can get out applications of the Hessian as well as this gradient information, and then you can do optimizations with full Newton and so forth. Generally, that's done matrix free because you don't want to actually compute these Hessians, but it's possible to do that as well. And I think in certain cases, you really want to get that information because then you get the 4 or 5 iterations of Newton as opposed to the God knows how many dozens or even hundreds of BFGS type iterations. The original work that really caused automatic differentiation to explode is by Andreas Grivonk, who sadly passed away a couple of weeks ago. It's really interesting to read that. There was work before that, but he kind of reopened it up to the world. And then I suggested a review article that I found on that's fairly recent on this. I can take any questions.
Are there any questions?
Thank you, great talk. Does the special care need to be taken when we're dealing with stiff ODEs? If we want to do the continuous version of things, if we like propagate forward, and then if we can't match the initial condition, propagate backwards, do things blow up, or are there methods of?
Sorry, I missed the beginning of the question.
So I'm trying to use my mic. Does special care need to be taken with stiff ODEs when trying to match the forward and backward pass? Because those things can differ if it's...
I don't think stiffness in particular. If you're using an implicit scheme, that means when you go back, you're actually solving these linear systems as opposed to just applying the Jacobian. There is the question, however, of when your ODE in the other direction may not be stable in the traditional sense, and so you need some kind of regularization or something else to actually go back to a unique solution. So simple thing like evolving the heat equation and then say, okay, I want to go back on the heat equation. You may not be able to always. So in the optimization process, but it's more that optimization process than the gradient process where you have to add the other terms for regularization.
Okay. This is working, right? Thanks for the talk, Barry. You mentioned that PETC can do second-order derivatives, but only in an operator sense? Do you mean like Hessian vector products, or does it compare?
Yeah, Hessian vector products, what we recommend. I honestly don't know if he coded it where you can compute them, but I know we do support it with the Hessian vector products. Yeah.
Okay, but never full, you don't compute full Hessian matrices.
I don't know if that's a capability that it has. It might actually have it.
Okay, thanks. Any questions on Zoom?
I have a comment. Don't use ADLC. It's terrible software.
No, it's terrible software, but it's Argonne from when I started at Argonne.
Okay.
That's why I have to mention it. But you're absolutely right.
They no longer contractually obliged.
It's terrible to code, but it's fast, no?
What's that?
ADLC.
No, it's slow.
Slow?
Compared to any modern implementation.
Oh, okay.
Badly engineered.
All right.
Yeah, it was one of the first attempts.
Yeah, like Stan's autodiff is about 10 times as fast as ADLC.
Okay.
So it's really pretty bad.
I tried coding things in ADLC, and I have nightmares to this day trying to change that code.
Well, that's just the C part. Right?
Yeah, not just.
General question. Do you have a comment on whether we should be using differentiable programming languages, or we should just be coding up this stuff, in Fortran or C or whatever language you like, and do it by hand? I mean, you sort of laid out the dichotomy at the beginning. Where do you think things are going? And for things like PDEs, where the overlap of the TensorFlow and PDE community is pretty small. I think it might be Chirag or somebody. It's like there's not many. That's a big gap to stretch across.
I think that there's a place for both of them.
Okay.
I think that numerical analysts who develop algorithms should and implement them in software should also provide the derivative information in their library. And generally, I think that probably should be done via the algorithmic approach. Now, users who have a problem that they want to do, where they're providing functions that are relatively simple, like these functions, define the model part, they should be probably using the automatic tools to get the derivatives for that. Can be done cleanly, easily. You don't introduce bugs because you do things manually. So I think there's a major role for both of them, but they're generally different groups of people would be doing the different ones.
Yeah.
Can I make a comment on that too? So I think you mentioned earlier that you can mix these two strategies. So what we do in Stan is we do exactly what you're talking about for the ODE sensitivities, but then that just calculates derivatives for the ODE integrator.
Yep.
Right? And then Stan's a differentiable programming language, so you can put that together with your noise models and everything else. And what we found ourselves doing over time is you can start really simple with this, which just take the algorithm and just auto-diff straight through like Runge-Kutta 4.5 or something. Takes up a ridiculous amount of memory, but it actually works. You can't control errors, things like that. And then we've gradually gone along and sort of unfolded the implementations of those special functions, right? So it looks like now you can call that, now we're currently, like Charles, in fact, the third person you cite up there is working on adding the adjoint methods to our ODE solver so that we can have them be more efficient at that level. But what we find is we're gradually like expanding what you're calling algorithmic differentiation and just using the autodiff as glue. I think just so other people don't get confused, if you read like Griewank's book, he defines automatic differentiation and algorithmic differentiation as synonyms.
Yeah.
So